let's look at first solving for the zero input response, or the zero input component of the output. So in this case, for our difference equation, again we set the right hand side to 0, and we're left using our operator notation with this polynomial in E, and then the zero input component of the solution I'll call y of 0, and now that's equal to 0. So since y0 of n, ey0 of n, and e squared y of n, and so on and so forth must have the same form, we'll try a solution of the form y0 of n is equal to c gamma of n. So again, we'll try as a solution an exponential discrete time signal. Just note here then that ey0 of n, which is y of 0 of n plus 1, then just becomes c gamma n plus 1, which I can write as c times gamma to the n, and similarly e squared y0 of n, go through these steps, I can write as c gamma squared gamma of n. In general, we have to find gamma such that q of gamma is equal to 0, so replace our advanced operators with gamma, and we come up with our characteristic equation, which is this. Okay. Q of gamma would be the characteristic polynomial, assuming, and we have different cases, just as we did for the continuous time case, assuming distinct roots. Then we can factor the characteristic polynomial as gamma minus gamma 1 times gamma minus gamma 2 times gamma minus gamma to the capital N for an nth order difference equation. And then so the corresponding solutions would be gamma equal to gamma 1, gamma equal to gamma 2, and so on and so forth. And so the general form of the zero input solution would be just a sum of these modes. The modes would be c gamma 1 to the n, c2 gamma 2 to the n, and so on and so forth. So our general solution would be c1 gamma 1 to the n plus c2 gamma 2 to the n plus c capital N gamma capital N to the lowercase n. Okay. Then we have to consider other cases. For a repeated root, if a root is repeated r times, then the corresponding modes are c1 gamma 1 to the n, c2 n gamma 1 to the n, c3 n squared gamma 1 to the n, and so on and so forth, until we get to the rth root, which would be cr n to the r minus 1 gamma to the n. And then the solution in this case would be a sum of these r terms. There may be other non-repeated roots, and then those corresponding modes would be added into the general solution. The other case we have to consider is if a root is complex. Again, you can write the solution directly in form of a complex power, but we can simplify it using actually Euler's formula. But if a particular root is complex and we're dealing with a difference equation that has real coefficients, then if gamma is a solution, then the complex conjugate of gamma must also be a root. And if we write the root in polar form, so if I write the particular complex root, I'll put a number on it. Let's call it gamma 1. If I write it in the form then gamma 1 e to the j beta, then the solution corresponding to this particular actually pair of complex roots, one at gamma 1, one at gamma 1 conjugate, I can write in this form. There's two arbitrary constants. C is one of them, and then times cosine of beta n plus theta. So again, gamma 1 is the magnitude of the complex root, and then the phase angle of the complex root then actually becomes my discrete time frequency, and then I have two unknown coefficients here, c and theta, which are determined by my initial conditions. So let's look at an example problem from the textbook. This is problem 3.6-1, where we're asked to solve the following difference equation: y of n plus 2 plus 3y of n plus 1 plus 2y of n, and then is equal to, setting the right hand side equal to 0, and we're given the initial conditions: y of minus 1 is equal to 0, and y of minus 2 is equal to 1. For a second order difference equation, we do need two initial conditions. Again, trying a solution of the form y of n is equal to c gamma to n, we get the following characteristic polynomial. Again, this comes directly from the difference equation. Gamma squared plus 3 gamma plus 2 is equal to 0. So you should be able to go from the difference equation directly to the characteristic polynomial. Notice how the advance here becomes an exponent in my characteristic equation, and then these coefficients become corresponding coefficients in the characteristic equation. This one is simple enough that I can factor it quite easily. In this case, it has two roots. They're both negative roots. Gamma would be equal to minus 1, and gamma is equal to minus 2. And so the general form of my zero input solution would be C1 minus 1 to the n plus C2 minus 2 to the n. And then now, to determine C1 and C2, I have to apply my initial conditions. Y0 of minus 1 is equal to 0. Plugging minus 1 into this equation, I get C1 times minus 1 to the minus 1 power plus C2 times minus 2 to the minus 1 power. Of to the minus 1 power is just the reciprocal, so the reciprocal of minus 1 is minus 1, so this becomes minus C1. The reciprocal of minus 2 is minus a half, so I get minus 1/2 C2. and then for my initial condition I know that this is equal to 0, so this will be one equation in terms of C1 and C2. For the other equation, I evaluate my 0 input solution at n equal to -2. Here I'll have -1 to the -2 power, or the reciprocal squared, that's going to be 1, and then I'll have plus C2 -2 to the -2 power. Again, that would be the reciprocal of -2, which is -1/2, but then squared, so I get plus 1/4 times C2, and that's equal to 1. And so this is my second equation. So I've got two equations and two unknowns here. From this first equation, I can immediately determine that C1 is equal to -1/2 C2. Take that, substitute into this expression, and I can find then that C1 is equal to 2 and C2 is equal to -4. So plug these values into these two equations and see that they satisfy the equations. So finally, the 0 input component of the total solution is 2 times -1 to the n minus 4 times -2 to the n. You might ask yourself too, in comparing this to continuous time systems, is this a stable system? You know, looking at the output for these initial conditions, is the output growing or not? Again, the answer is slightly different than you might expect in comparison to a continuous time system. For a continuous time system, with the roots both negative, that would correspond to a stable system. That turns out not to be the case here. There's another condition that the roots have to satisfy for discrete time systems, and so we'll take a look at that in the future.